What is a series? Well, let's start with a sequence. And this we just discussed. So a sequence is like this: A1, A2, A3, A4, etc. And we add and add. So what would this be? Well, you can either just write out the terms, which would be A1 plus A2 plus A3 plus A4 plus, okay? Or we can write it in summation notation as a sum, k equals 1 to infinity of ak. This is a series. Now, well, the first question I hope you are asking yourself is, how do you know if this is even, finite or infinite? Because you're adding up infinitely many numbers. There's no reason to expect that this is actually a number, right? So, well, question, how do we know if the sum of infinitely many numbers, which is what we're doing here, infinitely many numbers, is finite? And the answer hopefully doesn't surprise you, because we have talked about Maclaurin series and Taylor series. And the only real difference here is these are not power series. So we don't have a variable x in here. These are series of numbers. But the answer, what we do in a situation like this, is we look at partial sums. We look at the nth partial sum. And what is that in this case? Oops, I started to write partial sum. Okay, well, Sn, we add up to n. This would be a sum, k equals 1 to n of a k. Now, I will say there's no reason you need to start with 1. Just like with sequences, you don't have to start with 1 here. We can start at 10. We can start at 100. You can start at 0, minus 10, whatever. Okay, start at some integer, and then you keep on marching up, add them all up. This is a series. And then these partial sums, Sn, you notice this is a sequence, because for every n, you have a number out of this by just adding up the first n terms, or the up to term n, I should say, right? This is a number, okay? Add up infinitely many things. We don't know yet if it's a number or not, but you add up a finite number of numbers, this is a number. So we will continue our answer as if the sequence Sn is convergent, then the series sum ak, and this is notation you will see. Sometimes people will write a series without putting k equals 1 to infinity. They'll just write it like this, but I will write it here. Okay, then this series converges and the sum k equals 1 to infinity of ak is, well, it's the limit of the partial sum. So this is a limit as n goes to infinity of Sn. But what is Sn? It's maybe I need a little more space. It is a sum. K equals 1 to n of a k, like this. Okay, so this is what the sum of a series is by definition. You add up the first, or the up to the nth term. Okay, this gives you Sn. Then you take a limit. And this is if this is convergent, namely that if this limit exists. And there's another part to this, which is we know not all sequences converge, or If you look at it here, not all limits exist. So I will say if this diverges, I'll say is a divergent sequence, then the sum of AK diverges. Okay, so this being a divergent series means that this limit here, maybe I will underline it in green, this limit here either is infinity or does not exist for some other reason, like oscillates, something like this. Okay, this is what it means for a series to converge, and the sum of the series, which is what this would mean in terms of a number, is this limit, as n goes to infinity of the partial sum. I'll say this before we start examples. It is not that common to actually be able to calculate the sum of a series. So by definition, maybe I'll write this again. By definition, this, or you start anywhere. Okay, whatever, I'll start at 1. AK equals the limit as n goes to infinity of the sum up to the nth term of AK, okay? And this again, provided the limit exists. Okay, that's the definition, which I just erased, but it's very rare you can actually calculate this limit, because being able to write Sn, which is the nth partial sum, which is this part, in terms of a closed formula such that you can evaluate the limit, that's very difficult for almost all series. So as we progress through the series discussion, for almost all series we see, we will not ever know the sum. That's this. We're not going to be able to calculate it. We'll want to say, well, does the series converge? Does the series diverge? And we will have a number of tests that we go through. Or when we get to something called alternating series, does it converge absolutely? Does it converge conditionally? Or does it diverge? Okay, then again, by that point we'll have several tests we can use. For our initial discussion, we will look at some where we can get our hands on Sn. Okay. And the first few we will do right now. So let's go 1 to infinity of, say, cosine of pi k. Now what is this? Here, let me draw a picture. I'm thinking of a unit circle. This is 0, pi, we keep going around. Okay, so let's write some of the terms of this series. Well, when k equals 1, we have the cosine of pi. This is over here, right? This is minus 1. When k equals 2, we have the cosine of 2 pi, which is right here. This is 1. When k equals 3, we're back around here. Cosine of, well, pi again, although it's 3 pi, minus 1. When k equals 4, we're back here, plus 1. And then it's going to go minus 1, plus 1, like this. The next one would be minus 1, okay? Keeps like this. Well, another way we could write this exact same series, if you didn't want to have the trigonometry in it, you notice, maybe I'll do it over here, this series can also be written as follows. It's a sum, and then we have, it's just minus 1 to the k, okay? It's the exact same series. Well, what's happening here, or what is the nth partial sum? Let's compute a few. We'll do S1, S2, S3, S4, okay? What's S1? Well, we add up through the k equals 1. It's just the first term. S2, we have 1, 2, add them up. S3, we have 1, 2, 3. This is the k equals 3, add them up. This is k equals 1, 2, 3, 4. Add them up, we have 0, 0. And this sort of pattern, as you could imagine, continues. So we see Sn is either -1 if n is odd, or it's 0 if n is even. And now, well, this sequence, the limit does not exist. If we try to evaluate a limit as n goes to infinity of Sn, which is the definition of this thing, or you could also think of it like this, same series. This is, does not exist. Because it's oscillating. Okay? We see from this that this series here, this series diverges. Okay? This is using the definition. Okay. So I'm just adding up 1, 2, 3, 4, 5, 6, 7, like this, all the way up to infinity. Well, let's compute. Maybe I'll write the terms. So this is 1 plus 2 plus 3 plus 4, like this. So let's compute a few partial sums. S1 is 1. S2, 1 plus 2, which is 3. S3, I think I can fit it down here. 1 plus 2, plus 3, this is 3 and 3 is 6. I'll do one more. 1 plus 2, 3 plus 4. This is 5 and 5, this is 10. Now, there is a formula for, you see this looks like it's just growing forever, but there's a formula which I will not prove. There's a formula for the sum of the first n integers. It is n times n plus 1 over 2. Okay, this is, if you add up the first n integers, and you could certainly check it. If you did 1 times 2 over 2, you get 1 here. If you did 2 times 3 over 2, you get 3 here. If you did, let's do another one, 4. 4 times 5 over 2, 20 over 2, you get 10, like this. This is something that you could prove by induction in, say, a math reasoning course, but I'm not going to prove it. I'm just going to use the fact that this is the sum of the first n integers. And then we take a limit as n goes to infinity. Well, this we can calculate the limit quite easily. The numerator is growing without bound. We have a fixed denominator of 2. This limit is infinity, or you could also say does not exist. And what this means is that this series here, I'll write it below, this series, k equals 1 to infinity of just k, this diverges. Okay, so both of these we have illustrated. We have seen two divergent series that we used the definition to compute or to show that they diverged. This is the one, maybe I'll start at 4. And then I'll do 1 over k minus 1 over k plus 1. This series has a name. This is called telescoping. And I will mention why after we just start computing. Or after we see what happens, I should say, with Sn. Okay, so Sn. This is, well, I need to add up. In this one, Sn will not have, we will not have n things that we sum over because we're starting at 4. But you start at 4, start writing terms till you get to the nth. This will be Sn. Okay, well, we have 1 over 4 minus 1 over 5. This is for k equals 4. Then we have 1 over 5 minus 1 over 6. This is for k equals 5. Okay, k equals 6 is like this. And then we would have k equals 7. And finally, I will write the k equals n. I have to put dot, dot, dots because I can't actually write out to n. This would be 1 over n minus 1 over, let's see, n plus 1, like this. This is Sn, but the thing that you notice here, which is what makes telescoping series so nice to work with, is you see, look, minus 5 plus 5, these two terms add to 0. Minus 1 6 plus 1 6, these two terms add to 0. Minus a 7th plus 1 7th, add to 0. This will continue. This will be paired with something from the next term. And finally, this 1 over n will be paired with something from the n minus first term, right? Because that would be 1 over n minus 1 minus 1 over n. So you'll have a little bitty, well, it's not going to be little bitty, it'll just be there. You're going to have a minus 1 over n in the term right before that adds to 0 with the 1 over n. Okay, maybe I will erase this. All of these add to 0, and so we get that Sn is 1/4 minus 1 over n plus 1. And the beauty of this is we are able to have this nice sort of closed formula for the partial sum, which I said already, this is not something you can commonly do. Okay, now we can figure out if the series converges or diverges because I can calculate a limit as n goes to infinity of the partial sum. Maybe I'll write that in 2 steps. Sn, this is a limit as n goes to infinity of 1 over 4 minus 1 over n plus 1. And this limit is quite straightforward to calculate. 1 over n plus 1 goes to 0, this part. And 1/4 is just a number. This limit is 1/4. So we have found not only that this series, my telescoping series, converges because this sequence here of partial sums converges, but also we know its sum. So this series, k equals 4 to infinity of 1 over k minus 1 over k plus 1. The sum is 1/4. And in particular, this means that it converges. Okay, very nice. Now comes our first or named series. We'll have 2, well, I guess telescoping is named, okay? And I didn't mention, but I will now. It gets the name telescoping, at least I think. Those back in the old days, they used to have these telescopes, you'd stretch it out, and then you'd push it back in, something like this. Stretch it out, and then you can see far away, and then you can, like this. I think that's why it gets the name. All the middle stuff can. So you start with this big sum, right? Many terms, and then it just compresses down to just a couple of terms, and you can evaluate the limit. Now, geometric series is, we have 2 that will be very important. Geometric series right now. Another one coming is p-series, which we will see in the next video. So what is a geometric series? Well, let me give you an example. Here is one. Let's say k equals 0 to infinity of 5, 1/3 to the k. Okay, so let's write out some terms. When k equals 0, I have 5, and then I have 5 over 3, and then I have 5 over 3 squared. I'll put the to the 1, and then I have 5 over 3 cubed, 5 over 3 to the 4th, etc. Okay, the more general way to write this, or all of these, they have the same pattern. What does a geometric series look like? I'm not going to write it in summation notation at first because I really want to stress it looks of the form of it. So it looks like this: a plus ar plus ar squared plus ar cubed plus ar to the 4th like this, where, well, you need A to not be equal to 0 for this to make sense, right? Because then the whole thing is just 0. Okay, now A has a name. This is the initial term. If you are handed a series that you see begins at 0, so I could write this, and my series here is of this form. I could write it with the indexing, let's see, equals, with the indexing starting at 0 to infinity of A, R to the K, okay? But you might be handed something where the index doesn't start at 0, or you don't exactly see R to the K. You see some other things and you need to work with algebra to, we'll do something like that, to simplify. So you're not always handed it exactly like this. But your initial term is always the very first one, and then R, this is what's called the ratio, and R, as you move from one term to the next, you're multiplying by R. You can see that here. A is the initial term. As I move from one term to the next, I am multiplying by R. This is the geometric series. Okay, well, here's one example. Let us, right now, figure out what's going on with the convergence and divergence of this series. Okay, so let's consider Sn for the geometric series. Well, I'm going to have to do this in two cases. Okay, case 1, R is equal to 1. And you'll see why I'm breaking it into two cases in a moment. If R is 1, this is quite easy to figure out Sn, because every single term, comma, Sn is just A plus A plus A plus A, which is NA. Certainly the limit as n goes to infinity of Sn, which is a limit as n goes to infinity of n times some non-zero number, this will not exist. Does not exist. Okay? Because A is non-zero. If A is positive, it's going to infinity. If A is negative, it's going to negative infinity. So this, if R is 1, and then maybe I will move, in fact, after this, because I'm going to need some space. Well, maybe I'll start writing. If R is 1, immediately we know geometric series diverges. Now, if R is not equal to 1, let's look at Sn, and then I'm going to do a little trick where I multiply by Rsn. And let's write it out. Well, this is A plus AR, plus AR squared, all the way out to AR to the n, okay? And then this is, well, I'm just going to shift it. This is AR plus AR squared plus, and then AR to the n plus AR to the n plus 1. Do you see? Because what happened when I took this line and multiplied by R? Well, the A went to here, AR. The AR went to here, AR squared. This goes to here, AR cubed, all the way to here. This term, when you multiply by R, is this one, okay? Now, here's where I'm going to move to the top, because I am out of space at the bottom. Now, what am I going to do, though? As I move to the top, I'm going to take and subtract this line, this minus this. I'm doing this because what's going to happen? We're going to get a whole lot of cancellation, kind of like we saw in the telescoping series, except I don't get the cancellation within Sn itself, but it will allow me to solve for Sn. Okay, so I have, on the left-hand side, I have Sn minus R Sn. Sn minus R Sn. On the right-hand side, well, I have A. then cancels, 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 right? What I mean by that is adds to 0, and I just have minus AR to the n plus 1. Okay, we're in wonderful shape now because let's factor out an Sn. 1 minus r is equal to a minus AR to the n plus 1. Now, you see, I am in case 2, which means r is not equal to 1, which means I can divide, okay? And I can solve for Sn exactly. Oh, I'll leave it up. Sn equals a minus AR to the n plus 1 divided by 1 minus r. Or let's factor, I'll do one more little step, a 1 minus r to the n plus 1 over 1 minus r. If we take a limit as n goes to infinity of Sn and we get a number, this means the series converges, which I just erased. The geometric series converges to that number. And if I take a limit as n goes to infinity of Sn and I get does not exist, then the geometric series diverges. Okay, now, what's happening here? Well, maybe I will add colors. A, 1. Okay, everything I have made black has no n in it at all. So if I want to think about what's happening as n goes to infinity for my series, or for my Sn, my sequence of partial sums, all that I really need to think about is this. Okay? Now, we discussed this when we discussed sequences last time on purpose because I knew the geometric series was coming. So we have, and if you remember, this is 0 if absolute value of r is less than 1. And then we get D and E. I won't write all the cases this time, or well, I'll just put D and E because either went to infinity, or, for instance, if we had r as minus 1, it diverges because it oscillates. I won't necessarily write all the cases, but this would be if absolute value of r is bigger than 1, or if r equals minus 1. And then, of course, the limit is 1 if r is 1, but I am in the case where r is not 1. Okay, so this means we put this all together and let's make a statement about the geometric series. Okay, here we go. The sum, 0. I'll write it in this form. Okay, what we see from this calculation, so if we are in the case absolute value of r less than 1, this goes to 0, the limit is a over 1 minus r. So I will say converges to a over 1 minus r if absolute value r less than 1, and this diverges otherwise. Otherwise. This is what our work shows. So otherwise. Okay? So this is something you will see, for example, in the sheet of all the tests I will hand out. If you have a geometric series, you don't have to recreate this process of writing Sn as this, and then taking a limit when r is 1, r is not 1, like this, like I did. That was justification of really where this comes from. But anytime you have a geometric series, all you have to do, find a, the initial term, find r, the ratio, and then if absolute value of r is less than 1, you do this, a over 1 minus r. Converges? Okay, wonderful. If absolute value of r is bigger than 1, or equal to, I should say, bigger or equal to 1, diverges. And then you are done with the explanation. But you must say it's geometric compute absolute value of r, and then whether it's bigger than or equal to 1 or less than 1, make your conclusion like this. Here are two examples that are geometric, and they're both convergent, although we will see that. This is the first one we started with, and this one's a bit easier because we see it's exactly of the form a r to the k, starting at 0, right? So we see by looking at this here, my initial term a is 5. Okay, how do we get that? Well, it's directly in the form a r to the k, but if it's not, as it is not here, you evaluate the term at whatever the lowest index is in your sum. This gives me my initial term. And then r we see is 1/3. Absolute value of r is 1/3 less than 1. And I should say this is geometric. Maybe, oops, geometric. Here. Okay. We have r, absolute value of r less than 1. This means it converges. And the sum is a over 1 minus r. Okay, so let's calculate. 5 over 1 minus 1/3. Well, this, we don't want to leave it like this, right? We need to, this would be 5 over 2 over 3, or 15 over 2. So this series, the sum is 15 over 2. Now here, this is another one. You will notice my letter, I'm using the sum as n, not k. This really doesn't matter. We could be summing over j, or over I, over n. Whatever your letter is, it's fine, okay? Now, this one starts at 1, and we also don't see a r to the k. But we do have something geometric. For instance, let's start just writing out some terms, okay? What happens when n equals 1? Well, we have 7 over 10 squared, which is 7 over 100, okay? Then we see 7 squared over 10 cubed. Then we see 7 cubed over 10 to the 4th, etc. I could have algebraically manipulated it, but I wanted to write out some terms just as a first sort of example. Okay, now you see by looking at the terms, the initial term, a, is 7 over 100. And r is 7 over 10, like this. Okay, you see the r, because you multiply as you move one term to the next, you're multiplying by 7 over 10. Okay. And, this is also geometric. I don't know where to write. I'll write it here, geometric. Okay. Absolute value of r is 7 over 10, less than 1. This converges. And in the geometric case, we know the sum. It converges to a over 1 minus r, which is 7 over 100 over 3/10, right? 1 minus 7/10. This will be 7 over 3 times 7 over 3 times 10 over 100. We get 7 over 30, like this. So this sum is 7 over 30. Let's do one more of these geometric series where we find the sum. And this one, I will say, this was on an exam of mine from the past. Okay, well, this is geometric, but how do we see that? This is a 2 to the 2k, but we can, in this one, instead of writing out the terms, as I did in my last example, I will work with properties of exponents. So you see there's a 5. This part I'll leave alone for the moment. 2 to the 2k is 4 to the k, right? The property of exponents that I have used is, and we use properties of exponents, I would say, a lot when we work with series. But I've used, if you have a power to a power, you multiply. Well, how is is that here? Okay, on the one hand, this is 2 to the 2k. On the other hand, this is 2 squared to the k, right? Power to a power, multiply. Okay, 2 squared is 4, right? So now I have written this as a number to the k, and then with one more step, I can write this as a sum. K equals 0 to infinity. It's 5 times minus 1 over 4 to the k. Okay, technically that's another property of exponents like this, where you have minus 1 to the k over 4 to the k. It's minus 1/4 to the k. Okay, well, looking at this, we see it's geometric. We see A is evaluated at 0, it's 5. We see the ratio R is negative 1/4. Absolute value of R, positive 1/4, less than 1. So it is convergent. Well, I would certainly hope so, because we're told to find the sum, right? In any case, this will converge to A over 1 minus R, which is 5 over 1 minus a 4 is here. This is 5 over 5/4, which we invert, multiply. This is 4, okay? So this series converges to 1/4. The sum is 1/4. Excuse me, 4. I said it wrong. The sum is 4. Okay, very nice. Now, what do I want to talk about next? Let me erase this. I would like to talk about our very first test for convergence. And I will say it is probably the easiest test to use to see if a series, well, it's not a test for convergence. In fact, convergence will never be the result of this test. It's a test for divergence. It's the easiest test to use, but it's also a test that gets misused the most. But this is our first of the tests of series. This one is called the term test. But before I state it, I'm going to state something else down below. And this you could prove, is really not even that long of a proof, but it's more logical, we could just think about. And it says the following. So if the sum, again, you can start anywhere, of AK. I'll start at 0, you can start at 1, 15, 102, whatever for your bottom index. If this converges, then what must be the case about the terms? Now, this is different. This is not the partial sum. This is the limit of the partial sum. So what this is saying, if you have a convergent series, okay, right here, what must be the case about the terms as a sequence? Well, think about it. If you're adding up an infinite number of terms, eventually the terms will go to 0. Because that would say you're adding up an infinite number of terms, I should say, and you get a finite number. Then eventually the terms will go to 0. Okay? I mentioned this is not terribly hard to prove, but I won't. But this is definitely the case. Okay? You can prove it using partial sums. And if you look at a convergent series, the terms must go to 0. Now, this will give us our test. Well, I started with it this way. For those of you who have had math reasoning, or maybe you haven't had math reasoning, but you know something called the contrapositive, this is an if then. And what's the contrapositive of this statement? Well, contrapositive, you negate this, implies negate this. And we know that the contrapositive and the original implication are logically equivalent. Okay. If none of that meant anything to you, don't worry about it. But if it means something, then you can delight in the fact that we're using that logic here, or at least connecting it to something you know. Okay, the contrapositive, you negate this. It says this: if the limit as k goes to infinity of ak is not equal to 0, then the series of AK diverges. And this is called the term test. This is equivalent to what I just said about if you have a series that converges, the terms must go to 0. This says if the terms don't go to 0, you must diverge. And this is, as I mentioned, one of the easier tests to use because let's just do a few. This we've seen was what? Cosine of pi k. Okay, and then, this one we have seen of k. Okay, both of these we can use the term test, but let's even get to something that seems not something we have seen. And something that I would not want to try to write out what Sn is. Well, I don't know, we could do something like k squared plus k minus 2 over 3k squared minus plus 4. Okay? Now, term test. We may use the term test on all three of these. So here, the limit as k goes to infinity of the terms of cosine of pi k. Well, this is oscillating, right? The cosine of pi k, in fact, we were writing out, it's either 1 or minus 1, this sequence. So this does not exist. Okay? So in particular, if a limit doesn't exist, it's not equal to 0. So by the term test, the series cosine pi k diverges. Okay, this would be all the justification you would need. In fact, we will see much more advanced tests. We will see shortly that have more justification involved. This one, as I mentioned, is the easiest to apply. Just take the limit of the terms. It's not equal to 0. And this, so this not equal to 0 can be D and E. D and E is included here. Maybe I'll write that. D and E is included. So either the limit exists and is some number other than 0, or the limit does not exist. All of that is encapsulated in the limit not being 0. Okay, here, by the term test, this series must diverge. And you see, with this justification, so this particular series we have now justified twice, with this justification I never computed a partial sum. Similarly here, I can justify this diverging. Look at the terms. Well, this is infinity. Definitely, or you could say D and E, not equal to 0. By the term test, this series diverges. And finally, we'll do this one. This one is one that we haven't already figured out diverged using the definition. And this one, the limit actually exists. So here, if I take a limit as k goes to infinity of k squared plus k minus 2 over 3k squared plus 4, we know this limit is 1/3. Okay? How do you see that? Well, one thing you could do is just look at the highest power. It's polynomial divided by polynomial. The highest power, okay, they match. So it would just be this coefficient over this one. If you don't trust yourself to do that, you could, for example, divide everything by k squared, each term in the numerator, each term in the denominator, then take a limit and you will see 1/3. Okay. This limit is 1/3, which is not equal to 0, again, by the term test. And everything I'm writing out is part of the justification. You don't want to leave off quoting the test or leave off quoting what you need to check for a test. In this case, it's evaluating a limit. I'll just write the series because I'm running out of space. diverges, okay? So here, this is 3 examples of using the term test, but I will give you something to be careful about. The term test, well, which I wrote was equivalent to this statement about if the series converges, then the terms go to 0. It is not an if and only if. Now, what does that mean for us? Okay, so let me write this. It's important enough to take the time to write because this is where the term test is misused the most. Okay, so if the limit as k goes to infinity of ak equals 0, well, then the term test tells you absolutely nothing. 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 You cannot make any conclusion about the series. If the terms go to 0, maybe the series converges, maybe the series diverges. You have no idea from the term test. So let me just mention, and we will see this next time, using something called the integral test. I will do both of these, but I will tell you, this series diverges. It's called the harmonic series. I will introduce this next time, although I'm introducing it now, so I'll at least give you the name, harmonic series. We will see, diverges. However, this series converges. This is a p-series. Again, we'll see this next time. But why am I bringing this up today? I'm bringing this up today because look, the terms in both cases, the limit as k goes to infinity of ak is 0. Okay? So what you see, hopefully we're not going to make the mistakes I've seen people make before. And here, the terms going to 0, the terms go to 0, the denominator is growing without bound. The terms go to 0, the denominator is growing without bound. But this is a divergent series, this is a convergent series. So if you have the terms go to 0, okay, the term test tells you nothing. Very good. Let's keep that straight. The term test will only give you divergence. Now, there's 2 ways we can go about this. One way, so way number 1, is as follows. Well, let's look at the terms. The limit as k goes to infinity of 6 to the k plus 1 over 5 to the k. Well, you may not feel comfortable just looking at it and realizing that the terms are going to infinity. We have exponential on the top, exponential on the bottom. This is a bigger base. It will dominate. If you don't feel comfortable saying that, all we need to do is let's just divide by the highest thing that we see, as we would do with polynomials. This would be a limit as k goes to infinity. Well, I'm going to divide everything. The highest thing I see is 6 to the k. So I would have a 1 plus. This would be 1 over 6 to the k. And in my denominator, I have a 5 over 6 to the k. Right? I've divided every term, every piece by 6 to the k. Now you see I can evaluate this limit. This one goes to 0. The denominator is growing without bound. This one, as I have it written, it is exponential with base less than 1. So this also goes to 0. Right? This is something we discussed, but also you can remind yourself, if you have an exponential with base less than 1, the graph looks like this. What's happening? My numerator is approaching fixed 1, right? So I have a fraction. My numerator is going to 1. My denominator is going to 0. Well, this is going to be growing without bound. So this limit is infinity. Okay, just like I said, right? I said if you aren't comfortable thinking about that, we just divide. Okay, this limit is infinity, which is definitely not equal to 0. By the term test, my series of 6 to the k plus 1 over 5 to the k diverges. Okay, now let's discuss way number 2. Okay, well, if we look here at this series, we may write this as a sum of 2 series. So the first would be 6 to the k over 5 to the k plus the sum, and here. I need to go to 2, and then 1 over 5 to the k. Right? Term by term, right? We just add, we get this. So this is the sum of 2 series. Now, what is the case? If this series converges to a number, and if this series converges to a number, then this one will converge to this plus this. Okay, fine. But that's not the case here. Both of these are geometric. This one is a convergent geometric series. Because, well, the initial term, this is a good exercise, is 1 over 25, 1 over 5 squared. My r is 1 over 5, absolute value of r, 1 over 5, less than 1, converges, and we can calculate a over 1 minus r. But this one, divergent geometric series. A, which is 6 squared over 5 squared, is 36 over 25. R is 6 over 5. Absolute value of r, bigger than 1, diverges. Okay, so what's happening with this series? Well, this is a number, but this one diverges. It's all positive terms, so necessarily diverges to infinity. This thing diverges, okay, because this one does. This is another way. In a sense, I think the term test is easier. Okay, here I am. This question is really a question about sequences because it's asking us to use the term test. So what I need to do is think, in all of these, I just look at the terms, and I'm trying to figure out, it should be the case that only one of them, the terms, go to something other than 0. Either the limit of the terms does not exist, or the limit of the terms exists and is some other number than 0. Both of these, you see a minus 1 to the k, but what's happening is the denominator is growing without bound. So if you have a sequence, and this works for both of these, if without the minus 1 to the k, if the sequence is going to 0, well, then you add this minus 1 to the k part, and you're oscillating, but getting closer and closer to 0. So both of these, the terms go to 0. Term test tells you nothing, term test tells you nothing. Okay? This one, natural log grows without bound, so 1 over it goes to 0. Term test tells you nothing, term test tells you nothing, and term test tells you nothing. Now, I guess by ruling out A, B, and C, the answer should be D. But if you want to verify it, we certainly can. So the answer here is D. This is this weirdo we discussed in the last video. And by weirdo, I mean quite fun. As well as weirdos are, right? Especially in math. If we take a limit as k goes to infinity of this, this was E, right, which is not equal to 0. And so we can use, because it's not equal to 0, the term test, and I'll write it, term test, this series, k equals 1 to infinity, 1 plus 1 over k to the k diverges. But for the other 3, the limit of the terms is 0, so the term test gives you no information, no information, no information, like this, okay?